We have just seen that molecular orbital theory fails to reconcile the shape of a molecule with the atomic orbitals from which it is derived. We turn now to an elegant solution to this problem. Suppose that we assume that atoms do not form bonds with their atomic orbitals, but rather with orbitals which are formed through what we'll call a mixing of the atomic orbitals. What we are going to do here is take the three 2p orbitals of carbon, as well as the one 2s orbital, and transform them, or hybridize them, into what we will call hybrid orbitals, which are orbitals that have the characteristics of the atomic orbitals on which they were based. Importantly, the hybrid orbitals are all of equal energy. That is, they are degenerate, and they will have a geometry which is in accord with the experimental data. Now, let me explain this idea of orbital mixing, as it is a common point of confusion. What does it mean exactly to take an s orbital and three 2p orbitals and throw them together and mix them? I think the easiest way to explain this is through an analogy. Let's take a look at the graphs of two common mathematical functions. First, we look at the absolute value function. And now, we're going to go ahead and look at the cosine function. Right now, I have them superimposed. I'm going to go ahead and temporarily turn off absolute value of x, and then go ahead and turn absolute value on, and turn off cosine of x. Now, obviously, the graphs of the functions are quite different. Let's try and mix them together, and we will do this by multiplying each function by a coefficient, and then add those functions together to make a composite function. We will see that the sum of these two functions still retains some of the characteristics of the functions from which they are derived. Now here we have the graph of the absolute value of x plus 3 times the cosine of x. I will say that this function is 1 part absolute value, 3 parts cosine. I'm going to turn off the absolute value of x, and now we see just the function by itself. Now, let me go ahead and change the coefficient of the cosine of x from 3 down to 2. And now I'm going to go ahead and turn off the preceding function. This gives us the function absolute value x plus 2 cosine x. And the graph is similar to what we just saw, although we might say that it looks a little bit more or less like the cosine function than it did before, definitely less. And now let's go ahead and lower the coefficient of the cosine function even more. So now we're going to reduce the function to absolute value of x plus just 1 times cosine x. In essence now, this is equal part absolute value of x plus equal parts cosine of x. And the composite function looks even less like the cosine of x. And now finally, I'm going to reduce the coefficient by a substantial amount, by 20 times, to make it very small for the cosine of x. Let's say 0.05. All right. At this scale, it's very difficult to even see how the cosine portion of the function has an effect on the graph. I have to really zoom in before I even begin to notice any of the wobbliness. Let me go ahead and turn on the original absolute value of x. And you see, even at this very close scale, the cosine of x is having very, very little effect on the composite function. Let's go back to our hybrid orbitals. Remember, the shape of each atomic orbital is itself derived from a mathematical function, just like our absolute values and our cosines that we had in the previous example. And these functions are the wave functions. We can add these functions and multiply them by coefficients in a very similar way to what we just did with absolute value and cosine. When we combine the 2s orbital with the 3 2p orbitals, we ultimately get 4 hybrid orbitals, which are 3 parts p and 1 part s. We call these hybrid orbitals sp3 orbitals, since 1 s orbital and 3 p orbitals went into making them. Go ahead and take a look at the shape here of an sp3 hybrid orbital. Does it look more like an s orbital or more like a p orbital? Well, it should be clear that it looks more like a p orbital. This makes sense because if we looked at the recipe for creating an sp3 orbital, 3 of the p orbitals went into it, but only a single s orbital. We might say that this orbital has 25% s character and 75% p character. And this terminology, particularly referring to s character, will be used fairly often over the next few chapters. The bonding in methane can best be described as an overlap between the 4 sp3 hybrid orbitals of carbon with the 1s orbitals of hydrogen. Now we know from VSEPR theory that electron groups will tend to get as far away from each other as possible. The electron groups in this case correspond to the 4 bonds in methane. Recall that the other possible electron group that we encounter consists of lone pairs, and we'll talk about those later. Now, by using hybrid orbitals, we're able to come up with a structure that matches experimental evidence. In particular, each bond angle is 109.5 degrees, and the bond lengths are, on average, the same length. Now, apply what you have just learned to draw the orbitals for ethane and water. Take a moment to pause this video while you do this. Okay, enough about methane. Let's move on to a different molecule. Here you see a drawing of ethene, a compound usually known by its common name, ethylene. You will notice that in this case, each carbon atom is bonded to 3 atoms, 2 hydrogens and the other carbon. This is 1 fewer atom than what we saw for methane per carbon atom. You will also notice that the bond angles for this molecule are close to 120 degrees, another difference from methane, and the shape corresponds to one you should be familiar with about those carbon atoms called trigonal planar. So there's also a double bond present, but we'll come back to that later. In order for each carbon atom to bond into 3 different atoms, there's only a need, this time, for 3 hybrid orbitals. In this case, we mix the 2s orbital with 2 of the 2p orbitals. This gives us a total of 3 hybrid orbitals, and we will call those sp2 orbitals. The reason for this is they are made up of 1s and 2p orbitals. And then what about the 2p orbital that we didn't hybridize? It's still there, and it will have an important role that we will address in just a moment. Take a look at the geometry of our orbitals. The 3 sp2 orbitals, shown right here, have bond angles of 120 degrees between them. Furthermore, we can see that they all lie within the same plane. The unhybridized p orbital is perpendicular to that plane. We might ask which of these is lowest in energy, the electrons in the sp2 orbitals individually, or those that would reside in the p orbital. Since s orbitals are lower in energy than p orbitals, as we see here, it should make sense that the hybrid orbitals are somewhere in between in terms of the energy. So hybrid orbitals are associated with lower energies than p, but higher energy than s. Let's go ahead and look at all 6 atoms in ethylene and see how their orbitals may be combined. Just like with methane, the hybrid orbitals can overlap, with the 1s orbitals of hydrogen to form a bond. In addition, the hybrid orbitals of each carbon atom can overlap with each other, as we see here. Whenever orbitals overlap directly on top of each other, we call the resulting bond a sigma bond. Now, although we did not call attention to it before, all 4 bonds in methane were sigma bonds. Now, whenever we have a single bond, we can say definitively that any single bond must always be a sigma bond. Sigma bonds are generally the strongest type of bond, as they have the maximum overlap between the orbitals. In general, the less overlap you have, the weaker the bond. Now, what about the unhybridized p orbitals? In ethylene, these orbitals are parallel to each other. This gives us another type of a bond called a pi bond. Notice that the overlap in this case is less than for a sigma bond, at least according to this representation, and there's more than one way that we can represent a pi bond. Now, consequently, pi bonds, because they have less overlap, they tend to be somewhat weaker than the comparable sigma bonds. When orbitals overlap, we always get both bonding and anti-bonding molecular orbitals. When we looked at the hydrogen molecule in the previous lecture, we saw that the bond derived from overlap of 2 1s orbitals. This gave rise to a sigma bond. However, recall that there was also an antibonding orbital. Although we did not designate it as such at the time, it should more properly be called a sigma antibonding orbital. To show antibonding, we often write an asterisk after the Greek letter, be it either sigma or pi. Here we see the bonding and antibonding orbitals associated with the 2p orbitals in the 2 carbon atoms. When the parallel orbitals have the same phase, as we see here, smeared together, we get a bonding MO. And this is, again, just a single MO, meaning it can hold up to 2 electrons. However, when the orbitals are out of phase, for example, you had a blue orbital on the top over here on this one, a blue lobe on the top, and then for this one, you had the red lobe on top of the molecule. So when they are out of phase like that, we get an antibonding orbital. Now, we expect in an ethylene molecule that only the bonding MO is occupied by the electrons in the ground state coming from the source 2p orbitals. Now, since this is an energetically favorable interaction, the pi bond leads to a more stable molecule than the absence of such a bond would. Just like we saw in the sigma antibonding MO, the pi antibonding MO also has a nodal plane right between the 2 nuclei. Now we come to an important question. Why is methane sp3 hybridized while the carbon atoms of ethylene are sp2 hybridized? Now recall that in methane, the carbon atom is bonded to 4 different atoms. For ethylene, on the other hand, each carbon is only bonded to 3 different atoms. So this carbon, for example, is bonded to 2 hydrogens and the other carbon atom. So it turns out that the hybridization of an atom can usually be determined very easily. First, we count the number of atoms the atom we are interested in is bonded to. Now remember, we're counting atoms, not bonds. So there's 3 atoms carbon is bonded to here, and that would technically be 3 sigma bonds. Now, to that, we are going to add the number of lone pairs that that atom possesses. In all cases so far, we've seen that the carbon atom possesses no lone pairs. And then we add those 2 numbers together. So carbon is bonded to 3 different atoms, and it has 0 lone pairs. So carbon needs 3 hybrid orbitals in this case. Okay? So in this situation then, the correct number of hybrid orbitals you need is 3. So we would choose an sp2 hybridization. We need 3 hybrid orbitals. Since methane is bonded to 4 atoms, it needs 4 hybrid orbitals. sp3 is the correct choice in this case, since sp3 orbitals always come in sets of 4. So, in summary, if you need 4 hybrid orbitals, sp3 is the correct designation. If you need 3 hybrid orbitals, then sp2 is the correct designation. Now don't forget, hybrid orbitals can also be used to hold lone pairs, and we'll see an example of this later on. We will now look at the last type of hybridization, which is important for organic molecules. Suppose you have an atom which needs to bond to 2 atoms. As you might imagine, the solution will be to hybridize an s orbital and a p orbital, and that will generate 2 hybrid orbitals, which we designate as sp. And it also leaves 2 of the 2p orbitals non-hybridized. The carbon atoms in acetylene here shown are sp hybridized. Now let's go ahead and take a look at the orbitals for acetylene. In particular, you'll want to pay attention to the geometry of all of these orbitals relative to each other. So we'll take one carbon atom here, the one that's drawn a little bit lower, and you will notice that its 2 sp orbitals are positioned at 180-degree angles to each other. Now the unhybridized p orbitals are at 90-degree angles to the sp hybrid orbitals, as well as at 90-degree angles to each other. So this allows for the formation of 2 pi bonds, as we see here. The one between the p orbitals, which are going up and down, and a pi bond between the p orbitals, which are coming out of the screen at us. Now the triple bond ultimately consists of a sigma bond, and that's from a head-on-head overlap of the sp orbitals from the 2 carbon atoms, and 2 pi bonds formed by the parallel overlap of the unhybridized p orbitals from the carbon atoms. So let's ask ourselves a couple questions here. First of all, which should be stronger, a pi bond or a sigma bond? We've already addressed this issue earlier on. In sigma bonds, there's substantially more overlap of the orbitals than is the case for a pi bond. So in general, sigma bonds are stronger than pi bonds. However, the effect is additive. So when 2 atoms are joined together by both a sigma and a pi bond, that would be held together more strongly than, say, if you only had 1 single bond or 1 pi bond. Now we come to a more difficult question. Which should be longer, a sigma bond between 2 sp3 hybridized atoms or a sigma bond between 2 sp hybridized atoms? For simplicity, let's assume that the atoms are of the same type, say carbon. You should think about this a moment and pause the video before going on. Now let's make an attempt to answer this. An sp3 hybrid orbital looks much more like a p orbital than an s orbital. P orbitals are generally much longer than s orbitals if we were to measure them from the tip of one lobe to the other. It follows from this that the distance between 2 sp3 hybrid orbitals should be greater than that found between the 2 somewhat shorter and stubbier sp hybridized orbitals. So we say that sp hybridized orbital has 50% s character. It is even more spherically shaped than an sp3 orbital and consequently shorter. Now we clearly see how the hybridization relates to bond length in this table. In the case of ethane, both carbon atoms are sp3 hybridized, and this gives rise to the longest carbon-carbon bond of the 3 at 1.54 angstroms. The carbon-carbon bond in ethylene, which is formed by the overlap of 2 sp2 hybridized orbitals, is shorter than that of ethane, and then the carbon-carbon bond in acetylene is even shorter due to the greater s character of the hybrid orbitals involved in making the sigma bond. You will notice at this point that whenever 2 atoms are joined by a single bond, that bond is always a sigma bond. If we have a double bond, then one of the bonds is a sigma bond and the other is a pi bond. Finally, in the case of a triple bond, there is one sigma bond and two pi bonds. So to summarize, when we're looking at multiple bonds, the first bond between any two atoms is always a sigma bond, and any additional bonds are always pi bonds.